Alright, so this video is going to be part 4 of finding the radius and interval of convergence, and we want to find the radius and interval of convergence of this power series up on the board, the sum from n equals 1 to infinity of n times x to the n over 2 to the n times n squared plus 1. Okay, now this is not an easily recognizable series. We can't really make a p-series or a geometric series out of this, so we're going to have to use either ratio or root test. Okay, and well, we're going to have to use ratio test here because we're not going to be able to use root. Okay, it'd be pretty obvious if we were able to use root because everything would end up being to an nth power and it'd be really nice and all that good stuff. So for our first step, I guess I'll start outlining the steps so it might be a little clearer which step I'm doing when. I don't know. Let me know if it helps. But using ratio test, we take the limit as n approaches infinity of a sub n plus 1 over a sub n. Okay, let's go ahead and do that here. We get the limit as n approaches infinity, the absolute value of, well, a sub n plus 1, let's plug in an n plus 1 wherever we see an n, and we get n plus 1 times x to the n plus 1 over 2 to the n plus 1 times, this is going to be a n plus 1 quantity squared plus 1, and that's all going to be over our a sub n, which is just, this is our a sub n right here. So 2 to the n times n squared plus 1. Alright. Now we got to make this look a lot better because it looks like garbage right now. So what we're going to do is we're going to group up each little part, like the n, what went with that. What was the n plus 1 version of n? Well, it was that n plus 1 up there. So I grouped those together. Okay, we get an n, we get an n plus 1 over n. It's going to be multiplied by a x to the n plus 1 over x to the n. That's going to be multiplied by 2 to the n over 2 to the n plus 1. And that's going to be multiplied by n squared plus 1 over, we can FOIL that n plus 1 quantity squared out, make it look a little nicer, and then we have to add 1 to it, so we will end up getting n squared plus 2n plus 2. Okay, and we have to end that absolute value sign. Okay, cool. Now we can even put each one of these, we can kind of analyze it as a separate limit. Okay, that's one of our limit laws that we can do. So n plus 1 over n. We know the limit of that is going to be 1, so we don't need to worry about that. Now, here we have this n squared plus 1 over n squared plus 2n plus 2. Our highest power on both top and bottom is that squared. Okay, so we have n squared on top and bottom. The coefficients for each are 1. So the limit is going to be 1 over 1. That's 1. Now we have this x to the n plus 1 over x to the n. That is going to be just x, so I'll draw a little arrow up here so I have a little room, and this is going to give us just an x, so I'll put that in an absolute value sign. Okay, the n's go away when you divide this out. Now when you divide this out, the n's go away again, but now you're going to get a 2 in the denominator, so we just get from this limit the absolute value of x over 2. Now what ratio test tells us is that for this to be convergent, this needs to be less than 1. So we got to find for what values of x this will be less than 1. We do that by getting rid of these absolute value signs. And if we do that, then what we must do is say that this is greater than negative 1. Okay? And then to kind of finish off finding our interval here. Okay? We have to multiply everything by 2. We get negative 2 is less than x is less than 2. And I guess this whole part right here is just step 2, finding the interval and the radius. So we get our starting interval from negative 2 to 2. Now I say starting because we have to kind of refine this when we check the endpoints of the interval. We got to see if we're going to include either one of these. So that's not our final interval yet. Now we also got to find the radius, okay? And if our interval is going from -2 to 2, the center of that is going to be 0. And from the center, again, not really good at drawing curly brackets, as I wasn't in the last part, but from the center to one of the endpoints of the interval is our radius, and that's 2. So our radius is going to be 2 here. And great. So that is our second part. I'm going to erase this, so get it down quick. All right. Now we're on to step 3, which is going to be checking the endpoints on the interval. Okay. So we got to put each one of these endpoints into a series, into our power series here, and figure out whether they're going to make the series converge or diverge. Okay? So we're starting off with -2. Take the sum from n equals 1 to infinity of n times -2 to the n over 2 to the n times n squared plus 1. Alright, all I did was put a -2 in for x. Alright, now we're able to break apart this -2 to the n to help these the 2 over n cancel out, and we get n times -1 to the n times 2 to the n over 2 to the n times n squared plus 1. These 2 to the n's go away, and what we have left is just the sum from n equals 1 to infinity of -1 to the n times n over n squared plus 1. Okay? So now what are we going to be able to do with this? Well, test for divergence, you can kind of see that that's not going to work here, okay? We have that higher power of n on the bottom, so not going to happen. But we can try the alternating series test, and that's going to help us out quite a bit. So the alternating series test says that it needs to be decreasing, okay, b sub n needs to be decreasing, and the limit as n approaches infinity of b sub n needs to equal 0. Okay, first off, we need to identify what b sub n is actually going to be. Okay, this is our a sub n. To make a sub n into b sub n, we need to remove what is making this the a sub n alternating. Okay, and that's that -1 to the n. So b sub n is going to be n over n squared plus 1. Okay, now is this decreasing? Well, all we have to do is look at the next term in the series. So that next term in the series is going to just be n plus 1. So we put an n plus 1 wherever we see an n. We get an n plus 1 over n plus 1 quantity squared plus 1. And that's equal to n plus 1 over, we've done this before, n squared plus 2n plus 2. Alright, that showed up earlier. So, you tell me, is this going to be decreasing? Alright, well, you can kind of see that this denominator has changed more than the numerator did. Okay, for the numerator, we only added 1. For the denominator, we're not only adding 2, so that's already more than 1, but we're also adding 2n to this. Okay, so the denominator is getting bigger and bigger way faster than the numerator, so it is going to be decreasing overall. So that satisfies our first condition of the alternating series test. And lastly, we need to see if the limit as n approaches infinity of n over n squared plus 1. You can see here that since we have that higher power of n on the bottom, what you're going to have is an infinitely large denominator as n approaches infinity, and that's going to make this limit equal 0. Alright, now if you don't believe me there, if you still feel a little uncomfortable with that, you can divide every term by n squared, or you can use L'Hopital's rule, whatever you'd like to do. Okay, but anyways, that satisfies our second condition of the alternating series test. So this is convergent by the alternating series test. And that makes that so we can do a -2 is going to be included here. Okay? So, erasing again, so make sure you have all this down. And now we're going to plug in our second endpoint, which instead of a -2 here, we're just going to get rid of that negative sign. Okay, because our second endpoint is just 2. So we're plugging in a 2 for x. Okay? Now when we do that, the 2 to the n's cancel off, and we're just left with the sum from n equals 1 to infinity of n over n squared plus 1. Okay? Now, if you're not really sure, you can't like tell immediately what to do with this, then use that checklist that I talked about when trying to figure out if a sequence, or a series is convergent or divergent. Okay? Use diclar. Okay? Can we use a test for divergence here? Okay, that's the D. Well, no, we can, but it's going to equal 0, so that's not going to work. Next is the integral test. Are we going to be able to do an integral test here? And yeah, we will, because you can see that this is kind of an easy U substitution. So let's do that. We can do the integral from 1 to infinity of x over x squared plus 1 dx. All right, and well, now we're just going to set u equal to x squared plus 1. That means that du will be equal to 2x dx. Since we don't have a 2, we can divide that over and just get du over 2 equals x dx. All right. We also need to figure out what our bounds are going to be. Okay, we got to change those bounds. And well, when x equals 1, because that's our first bound, what will u equal? We can just plug that right in here. We get, well, 1 squared plus 1, that's 2, so u will equal 2. Now when we have x equal to t, all right, which is going to be our other bound, because I didn't write out the limit yet here, but I will in a second. When x is equal to t, well, t is approaching infinity, so if you're squaring it, adding 1, whatever, it's still going to be approaching infinity, so u is also going to equal t. All right, so now I can write out our bounds here, and of course I need to write out a limit. So limit as t approaches infinity, the integral from 2 to t of, well, now we're just going to have that u on the bottom, and we're going to have a du over 2. Okay, so we get a 1/2 out front, and we're going to have a 1 over u du on as the integrand. Okay, so we get here the limit as t approaches infinity of, this is going to be 1/2 the natural log absolute value of u evaluated from 2 to t. Okay, then just doing this out real quick, you could probably already see the answer. The limit as t approaches infinity of 1/2 times the natural log absolute value of t minus the natural log absolute value of 2. Well, as t approaches infinity, this will also approach infinity, so this is going to be divergent by the integral test. Okay, so what that's saying is that we're not going to include this endpoint, and that's going to be our final interval of convergence. And of course, we also have our radius of convergence in there. So that's going to do it for this video.
So if this video helped you, make sure to leave a like and subscribe by clicking my icon in the top left. You can also view the playlist for sequences and series, the explanation video for radius and interval of convergence, in the next video in the series. Lastly, if these videos are really helping you and you would like to consider supporting me, I have my Patreon linked in the description down below, along with some other pretty cool links that you should definitely check out. See you soon.